Okay, so in the last video, we talked about figure 1, and we are relating all 4 of these different quantities. Represented particles, volume at STP, and mass all relate to moles. And so using moles as the bridge, you could relate any of these other 3 pieces. So now we're going to try a few examples. So we're going to start with some various quantities. So let's say that we have 30.5 grams of carbon dioxide. So we have a known mass, which means for this example, we are starting here. And I want to get us to these other locations, so we're going to look at how many molecules are in this sample of carbon dioxide and what is the volume in liters at STP. So what is the volume at STP? So what we're going to do, let's work with going to molecules first. We always start with our given value, and in this situation, it is the 30.5 grams of CO2. And this is going to be a dimensional analysis type problem. The things that we learned early on in the year, they're coming back. So if we look at our figure 1 up here, we see that to go from grams to molecules is not a one-step thing. The mass to represented particles, there's no direct arrow. But we can pretty easily find how we need to do this. So we're starting at mass, and so the only place we can go for a mass is to moles. And in order to do that, we are putting 1 mole on top and the molar mass of this compound on the bottom. So 1 mole goes on top, and the molar mass will be here. But this is the one number that we have to calculate because the molar mass is different for every compound. So we're going to set up our table so we can visualize what's going on. So CO2 molar mass, quantity, and total. So I'm making my table here. In the first column, there is carbon and oxygen in this compound. Next, I have to look at my periodic table, and carbon rounds to 12.0. Oxygen rounds to 16.0. Those are both in grams per mole. The quantity comes from the chemical formula. So we see that there is 1 carbon and there are 2 oxygens. And remember what we're doing here. We are essentially multiplying these 2 numbers to get a total, and these 2 numbers to get a total. After that, we will add the entire column together to find the mass of the compound. So 12.0 times 1, that's 12.0. 16.0 times 2, 32.0. And the total mass of this compound is 44.0 grams per mole. Now, this is the number that I want to put right here. 44.0. So at this point, we can see that grams will cancel. And now we have units of moles. So we were at mass, we used this conversion, now we're here. We are looking for the number of molecules, which is representative particles, which means we need to be here. So we're going to follow this arrow, which means this is the conversion that needs to be used. So let's go ahead and write this in. So we are going from moles to representative particles. We need moles to be on bottom, and we need 6.02 times 10 to the 23rd to be on top. Now this is specifically a number with a unit. Representative particles is just the basic idea. The unit here is the molecule because CO2 is a covalent compound. We see that moles will cancel out and we're left with molecules. So we put this in our calculator, and you want to be very careful, especially with the scientific notation. Your calculator probably needs some parentheses. So we're doing 30.5 divided by 44 times Avogadro's number. And we find that we have 4.17 times 10 to the 23rd. And our units are molecules. And we're talking about carbon dioxide. So in this mass of carbon dioxide, there should be this many molecules. We could also figure out what is the volume that this is going to occupy. And for that, you're going to use the same starting point, the same given value. That's 30.5 grams of CO2 over 1. Now we're here again, mass, and so we have to get to moles first. That's the only place we can go. And so this first conversion factor is the same as in the previous question. And we already found the molar mass, so we just plug it in. So we're looking for volume at STP. We're going to follow this arrow, which tells us to use the conversion 22.4 liters over 1 mole. And so we go back and look, grams cancels, moles cancels, and we're left with units of liters, which is the appropriate unit for volume. In the calculator, all you have to do is type 30.5 divided by 44 times 22.4, hit enter. We find that the volume here is 15.5 liters. So you should have room for another example like this immediately below. So let's take a look here. You should have some room. But in order to keep this figure 1 in the picture, I'm going to erase the work that we did here. So in this next example, let's say that we are starting with the volume of a gas. Let's say that we have 84.1, and this is liters of CH4, and specifically this is at STP. And I want to know what is the mass of this sample, and I want to know the number of molecules in this sample. So for the first calculation, we're looking for the mass. We always start with our given value, and in this case it is 84.1 liters of CH4. Put it over 1, that lines it up well for our dimensional analysis. So in the first conversion, we need to go from volume to moles. And so we follow this arrow right here, and that tells us that 1 mole should be on the top and 22.4 liters should be on the bottom. So here, liters cancels out, and that gives us units of moles. So we are here in the middle of figure 1. But what I really want to know, what is the mass of this sample? And so I need to go from moles to mass. And in order to do that, it's this conversion right here. So 1 mole goes on the bottom, and the molar mass goes on the top. Just like in the previous example, we have to figure out the molar mass for this compound because it's different for every compound. For CO2, it was 44, but for CH4, it's going to be something different. So let's set up our table. In the first column, I'm writing my elements. I know there's carbon, I know there's hydrogen. In the second column, it's the molar mass. This is from the periodic table. 12.0 for carbon. For hydrogen, it is 1.01. The quantity comes from the chemical formula. So we see 1 carbon, we see 4 hydrogens. Multiply your rows. So 12 times 1, 12.0. 1.01 times 4, 4.04. So when you add these together, we end up with 16.04, and that's grams per mole. We do have to pay attention to our significant figures. And we're talking about addition here. And in addition, remember the number that has the fewest digits after the decimal decides how many digits can be after the decimal. So for this one, it's 12.0. So that says our answer can only have 1 digit beyond this decimal. And so this 4 is going to get dropped off. We want to make sure that it's not going to round up, and it's a 4, so it's not. And so we're going to get rid of the 4, and we have 16.0. So let's bring this number up here. 16.0 grams. Moles will cancel out top and bottom. And now we're set to go to our calculator. Don't go to your calculator until you've got it on paper. So 84.1 divide by 22.4 times 16.0. we find that this sample of CH4 should have a mass of 60.1 grams. So next up, we could also look at what should the volume be, what should the number of molecules be when we know the volume. So as usual, we start with our given value. I'm going to erase this chart so that we have a little more room to write. So 84.1 liters was our given value. And in order to find molecules from liters, we have to do two steps. So the first arrow tells us to use this conversion, 1 mole over 22.4 liters. The key that this works, the clue is that liters will cancel, and now we have moles. We are here. And we want molecules, which means we're following this arrow, which tells us it should be 6.02 times 10 to the 23rd over 1 mole. We need to keep units in this dimensional analysis setup, so I'm going to specify that CH4 is molecules, and I'm going to cancel out the moles. And so we put this in our calculator, 84.1 divided by 22.4 times Avogadro's number in parentheses. And you should come up with 2.26 times 10 to the 24th. And that's molecules of CH4.